Now, yesterday or the previous sessions, we talk about work, and basically, work is when we have a force which acts on an object, and that force causes a displacement of the object. Now, if the force and the displacement is along the same direction, we know that it's simply the magnitude of the force multiplied by the magnitude of the displacement. However, in most general applications where the force and the displacement are no longer on the same direction, we solve for work as the magnitude of F, D, and then the cosine theta. And always remember that the angle theta is always measured as the angle between the two vectors. In this case, that's the angle between the force and the displacement D always. Alright? So now I'm hoping you do have some like getting to know work when you solve the several problems. So notice that in a single scenario, we can actually solve for many work due to each of the forces that acts on our problem or our body, for example. So we did this sample problem number 1, number 2. This one also was given as an assignment, and then this one was your practice problem, and I promise to give the solution later this day. Okay, and I think, yeah, this was the other problem also that you can solve out of your choice, either of the two problems. Now, I'm hoping you do understand work so much, because if you understand work, the concept of power would be very easy for you to grasp. So what is power? So to illustrate what power is, consider this case. We have here Zoro and Usopp. So they are both lifting. As you can see, it's not really clear, but let's just say they are both lifting an object with a mass of, say, just going to have mass 1 to be equal to 10 kilogram ball, and Usopp also do the same thing. He should lift a mass of 10 kilogram, and let's just say for simplicity, both of them have to lift that 10 kilogram object up to a height of, say, 0.5 meters. So this one right here is 0.5 meters, and also Usopp has to do the same thing. He has to lift the 10 kilogram I don't know what that is, a ball or something, to a height of, say, 0.5 meters. So they both have to lift the mass of 10 kilograms to 0.5 meters. Now in this case, Zoro lifted it in merely 2 seconds. That means to say 1, 2, the ball is already here. While Usopp lifted it in 4 seconds. So 1, 2, 3, 4 before the ball reaches the tip of the 0.5 meters measurement. Now in this case, class, what we will say in this case is Zoro is more powerful. Let's just say in a more colloquial term, more powerful than Usopp. So what do you think is power, or how does this situation tells us about what power is? So powerful, or let's say power in physics. Now, one of the things that you should note here, class, is both Zoro and Usopp. I think you have a question here. Zoro and Usopp did the same amount of work, because basically they both lifted an object with a mass of 10 kilograms, and each of them have to lift that to a height of 5 meters. So I'm just going to resketch again the problem. Both of them have to lift that to a height of 0.5 meters. So I'm going to duplicate that here so that you'll understand what I'm talking about. So both of them has to lift 10 kilograms to 0.5 meters, and when we actually solve for the work here, the work done by Zoro, as you can remember, work is just F D cosine theta. Now, in this case, class, the force that Zoro has to apply is directed upward to lift that object. So I'm just going to illustrate that one there. And also, the displacement is also moving up, since you want that object, to move up. That means to say that in our equation, this will reduce to FD cosine of the angle between the force and the displacement in this case is just 0, and cosine of 0 is 1. That means to say we have the work done by Zoro to be simply given by F and the displacement. However, class, you have to remember this one. This will be helpful in your problem solving later. This force here, this F that you need to apply to lift an object is simply equal. I'll just write it here. The force needed to lift an object is just equal to, at least the minimum force, is just equal to the weight of that object, So in this case, this is generally true, and this is a concept that you have to apply in your problem solving later. That means to say that the force here will simply be the weight of the object multiplied by the displacement. The weight of this object is just the mass times the acceleration due to gravity and the displacement. Okay, so the mass is 10 kilograms. The acceleration due to gravity is 9.8 meter per second squared. So that right there will result to 98, and the displacement is 0.5 meters. So the the work done by Zoro in this case is simply half of 98, and that is how much? It's 49. Yeah, it's 49. The unit is kilogram meters times meter per second squared. This term here results to Newton. Newton times meters result to joules, which is the SI unit of your work. Now, if you think about it, when you try to solve for the work done by Usup, the same thing actually happens, class. Everything is the same as right here. So Usopp has to do the same thing. He has to apply a force of at least the weight of this object, and since the mass of the object is 10 kilograms, so the weight would be the same, he also has to apply that force upward and cause the object to move by a displacement of 0.5, so you'll end up with the same work. That is why in this case they actually did the same amount of work. However, as we said earlier, Zoro is more powerful than Usopp in this situation. Or we say that Zoro is operating at a higher power than Usopp. So what do you think is power about? Since they both do the same amount of work, the only variable that varies here that is very apparent is the time. I'm just going to highlight this here. Power is related with the time. So power is simply the rate at which your work is being done, or in more colloquial terms, this simply quantizes how fast is the work being done. Mathematically, it's expressed as the change in work over the change in time, or simply the work over time. Now, I would just like to emphasize some of the things in the equation. So when the time decreases, that means to say we're doing a constant work or a specific value for work, yet we do it in a very small amount of time, the power in that case increases, since power and time are inversely related. So that means to say in this case, since Zoro did it in just 2 seconds, that means to say his power is large because power is just the rate of work over time. In Usopp's case, the time slightly increases, so the power decreases in that case. Okay? Now, the SI unit of power is watt, and hence this classic meme. So we have here Hagrid telling Harry that you're a unit of power. And then Harry is just saying, I'm a watt, because watt is basically your SI unit for power. So let's put it a little bit of a laugh. I know I deliver the joke badly, but anyway, the SI unit of power is watt or watts, the same as watt na nasa inyo light bulbs, which we will relate with our discussion soon. Watts sa inyo ang mga appliances, so it's the same watt, power wattage in that case. So 1 watt by definition is just 1 joule per second. So I just felt like I have to write everything na mga SI units. So again, 1 newton, just to iterate some things. 1 newton is just 1 kilogram times meter per second squared, and 1 joule is just 1 newton times meter. And now another na more of a conversion factor in relating SI units is 1 watt is simply 1 joule per second. Okay, so for example, another British unit na you will encounter, class, is the horsepower. The same horsepower that you have in your air conditioners, which we will also discuss along the way later. So your horsepower is a British unit, it's not an SI unit, but in terms of SI units, 1 HP is equivalent to, we'll use this in class 746. Okay, so every time you encounter HP, we'll use 746 instead of the 745.7. So this is what we will use, so 746. So what does it mean? So how do you visualize 1 horsepower? So 1 horsepower is just like this. If you have a weight of 550 pound na mass, and you have to lift that 550 pound mass, kasi British unit nga siya, diba? To a height of 1 foot, and you have to do that lifting in 1 second. That's how fast the time should be. Then that work to do that, that power to do that is exactly what we call the horsepower. Again, 1 horsepower is the power exerted when you have to lift a 500 pound weight to a height of 1 foot, or approximately just a like a ruler height, in a matter of 1 second. So that power is 1 horsepower. Now I know we're not used to the pounds and the foot thing, so just to put context, your 550 pound is approximately this one, class, or 250 kilograms. So that's a very heavy na object or mass. 250 kilogram, your 1 foot is almost 0.3 meters, or just your 1 ruler. So imagine you have to lift almost 250 kilograms. So kung rice pa na siya, murag 5 ka sako nga bugas, to a height of 1 ruler in a matter of 1 second. That power is 1 HP. Okay, so just for you to imagine that one. But again, HP is not an SI unit. I would just put here, this is a British unit. So every time you encounter that one, you have to convert that into watts, which is the SI unit of power. So for our first problem, this will be very easy. Problem 1 is we have an aircon that is rated at 1 HP. How much work can it do in an hour? So power is simply either the change in work over delta T, or simply work over time. So power, I'm going to use the work over time definition here. The problem is asking for the work, and the 1 HP, I'm hoping you can recall from what I just talked, this is actually a unit of power, but this is not in this is not an SI unit. Why power? And 1 hour is, of course, a unit of time. Now if I'm going to solve for work, I have to multiply both sides by time, and in doing that I will get power times time is equal to the work, right? So work is just equal to the power, 1 HP, multiplied by the time, that's 1 hour. Now notice that your units did not make sense, so that's why we have to do some what's this, more like dimensional analysis in the same manner that you have in your chemistry. You have to recall that, as I've said earlier, your 1 horsepower is just 746 watts. Now for your 1 hour, I'm hoping I don't have to go to step by step, but 1 hour is 3,600 seconds. So you have to figure that out, the step by step process, why you arrive at 3,600. So that means to say 1 HP, we're going to substitute that with the SI unit, that's approximately 746 watts. Sorry, double T. 1 hour is 3,600 seconds. And remember, 1 watt is just, so gananing 1 watt, 1 joule per second. So that means to say this will be 746, the watt parts will be joules per second. You multiply it by 3,600 seconds, and in doing that, the seconds will cancel out. That will give you 746 times 3,600. That will give you 2685600. The unit is joules. So that's gonna be 2,685 joules. So this is the work. Now we will relate later what does this mean, but in simple terms, this is the work class that your aircon is doing in removing the heat sa imuang kwarto or sa imuang room. Dako kay siya nga amount of work, no, 2,685 joules. Okay, so this is how you manipulate power. I know it's not very cannot bitong deep discussion on what power is or what does this mean when an aircon do this amount of power, but we'll relate this once we are finished with the discussion on energy, because it will all make sense when we will be talking about energy. Okay, so for problem 2, this is just a trick question. I'm hoping you can answer this one. Okay, let's try to solve this problem. A person holds an 80 Newton weight 2 meters above the floor for 30 seconds. The question is, the power required to do this is A, 80 watts, B, 40 watts, C, 20 watts, D, 10 watts, or E, none of the above. Now let me just illustrate the problem for you. Of course, I'm a great artist. That's my personal claim. Okay, if I have a person here, okay, that's okay, like this. Okay, it's like that, and that person holds some weight. I'll just do it like this one or that. Okay, a person holds some weight there, and the weight of this object is 80 newtons, and that is 2 meters above the ground. So just to help you illustrate, so wow, this is really weird. 2 meters na tao taas sa padan niya class, no? 2 meters, murag maka-insecure yung height. Okay, like that. Okay, let's just say that's 2 meters. Take note, a person holds an 80 Newton weight 2 meters above the floor for 30 seconds, meaning to say, it's just like more like exercising na iyang gipasaka sa taas. The weight is being lifted upward for 30 seconds. It's not actually lifted, but he just held it in place. The question is, what should be the power in that case? So I will probably give you 30 seconds to think about it, but the answer is none of the above. Why none of the above? In the first place, your equation for power is just work over time. Now work, if you can recall, I'm going to expand this one. Work is just F D cosine theta all over time. So basically what I did here, class, is to simply break down the expression for work as FD cosine theta. So this term here is the same as this term. Okay, so I'm hoping you'll not get confused with that. The point that why I break that down is, since the person is merely holding it, it means to say that the person is, yes, the person is applying a force. It's just that the D is 0. There's no displacement there. The person just have to hold it in place. So there's really no displacement at all. The person did not move it up or down. It's just holding, so the displacement is 0. And of course, that means to say the work will also be 0. Or the person is actually doing no work in that case. So work is just 0. So therefore, if this term is 0, then your power also is 0. That's why the answer for this is none of the above. Alright? So for the problem number 3, this is quite challenging. Your job is to lift. This is on your own now. Your job is to lift 30 kilogram crates, a vertical distance of 0.90. So that means to say, you have here some crate like that. The mass of this crate, this is a mass of 30 kilograms. And then your job is basically to lift that crate a distance of 0.90 meters. So let's say if this one right here is your reference or floor, you have to lift this at a height of 0.90. That height is 0.90 meters from the ground onto the bed of a truck. So you have to load this on the truck onto the truck. The question, class, is how many crates? So meaning to say, this is not just one crate, probably a lot of crates here, and each of them weighs exactly 30 kilograms. So how many crates would you have to load onto the truck in a time of 1 minute for your average power or power to be you used to lift the crate to be equal to 0.5 HP? So that's the question. How many crates would you have to lift so that you'll have a power of 0.5 HP? Now the given are there, so I'm going to write just for you to help you solve the problem. Take note na, as I've said, no, the force required to lift an object, the minimum force required to lift an object is simply equal to the weight of that object. And this is an important concept which you have to use in solving this problem. And of course, in lifting this object, that means you have to apply a force upward. Also, the displacement would move upward. And in doing this, you're doing work. The problem is giving you this should be your power, this should be your time. So basically, everything is laid out for you. It's just that you have to piece the pieces together. Okay? So I'm not saying that you have to submit this one, but it would really help if you will try to practice on this problem. So this is the end of our coverage for the for the second quarter exam. You'll expect some basic problems in power. So maybe problems like this one, kana bitang one-liner problem lang. Your problem solving will heavily focus on the free body diagrams and the application of Newton's second law. So that's it for the day 3, final day of your online asynchronous week.